back.
This is our old friend Robert Boyle, the same Robert Boyle that we previously credited with Christianizing Epicurean atomism so that it would not be quite so distasteful to Christians. In 1660, Boyle published the text you see pictured on the right here, New Experiments Physico-Mechanical, touching the spring of the air and its effects. This text contains the reports, the results of 43 separate experiments that Boyle conducted on both physical and physiological processes at both normal and reduced atmospheric pressures. Before we get too much farther into this, there are several things I want to make you aware of. Number one, if you look at the title of Boyle's text, this incredibly important work, you'll see the phrase, the spring of the air. When Boyle uses the phrase, the spring of the air, he means pressure. So keep that in mind. The spring of the air equals pressure. Secondly, Boyle performed experiments at reduced atmospheric pressure. In order to do this, he first had to develop a pump that would allow him to reduce atmospheric pressures. And in conjunction with Robert Hooke, another physicist whom you'll learn a great deal about next year in physics, Boyle and Hooke developed just such a pump. Next, in several of the experiments, Boyle talks about the behavior of the barometer. The barometer had only been developed about 16 years prior to the publication of Boyle's work by the Italian physicist Evangelista Torricelli. And finally, Boyle investigated the effects of reduced pressure on a wide variety of phenomena. He examined the effect of reduced pressure on magnetism, how it affected sound, behavior of a pendulum, how reduced pressure affected the evolution of gases from liquids, and he even looked at how reduced pressures affected the behavior of smoke. According to Boyle's law, if I have a fixed mass of gas and I keep that gas at a constant temperature, well, the pressure and the volume are going to be related indirectly. In order for us to understand what that means exactly, we need to make certain we all understand what an indirect mathematical relationship is. In an indirect mathematical relationship, the variables travel in opposite directions. In other words, if one variable increases, the other one by necessity must decrease. Need a practical example? How about this? How about the number of hairs on my head and my age? As my age increases, the number of hairs on my head decreases. Those two variables are related indirectly. Well, in the context of Boyle's law, what that means is if the pressure that I exert on a gas is increased, then its volume is going to go down. The counterpart to that is if the pressure on a gas is decreased, then the volume is going to increase. So, pressure down, volume up. The mathematical expression associated with Boyle's law is V1 P1 equals V2 P2. V for volume, P for pressure. The subscripts 1 typically refer to the initial volume or pressure, the subscripts 2 with the final volume and pressure. You want to make sure that when you're working with that equation that whatever your units are for a particular volume, let's say, that the units are consistent on both sides of the equation. In other words, if V1 is expressed in milliliters of a gas, then V2 has to be expressed in milliliters as well. On the other hand, if the pressure is expressed, P1 let's say, is expressed in atmospheres, make sure that P2 is expressed in atmospheres as well. You cannot mix different units of volume or pressure. It simply won't yield correct answers. And what you see below that is one of the more commonly used rearrangements of Boyle's law. However, based on the fact that you are high school sophomores, soon to be juniors, I do expect you to be able to arrange Boyle's law, V1 P1 equals V2 P2, to solve for any of those variables. Let's take a look at a couple of sample problems now. Here's our first Boyle's law sample problem. It reads, a potato chip bag has a volume of 315 milliliters when it is packaged at sea level where the atmospheric pressure is 101.325 kilopascals. Assuming the bag doesn't explode, what would its volume be at Denver, Colorado, the so-called Mile High City, where the air pressure is 84.3 kilopascals? Assume there is no change in the temperature. Anytime we read a problem where it says there's no change in the temperature, we're pretty well guaranteed that this is a Boyle's Law problem. Beyond that, the most difficult aspect of many gas law problems is the identification of the variables. In other words, what information is given, what are we looking for? Up here in the first line of the problem, it talks about a chip bag having a volume of 315 milliliters. Milliliters is an appropriate unit of volume for a gas. And because this is the first volume that we read about in this problem as written, we're going to call this or identify it as V1. It says that this package of chips is produced at sea level where the pressure, air pressure, is 101.325 kilopascals. That's the first pressure we read about, so we're going to identify this quantity as P1. From there, we're asked, what would its volume be? Volume, that's our unknown. That's what we're going to be looking for, V2. That's our unknown. And finally, we're told that all of this is going to be at a second pressure of 84.3 kilopascals. So this is P2. Okay, we've got 3 of the 4 variables from Boyle's Law identified. We know that we're looking for V2. So at this point, all we need to do is write the expression for Boyle's Law. V1 P1 equals V2 P2. We need to rearrange it to solve for V2, and what that's going to yield is V1 P1 over P2, and that's going to yield V2. Before we even substitute and begin to crank out an answer, let's ask ourselves, what's really going on here? Well, we're looking at a reduction in the pressure. We're going from 101.325 kilopascals down to 84.3 kilopascals. Based on what we have just previously examined with regard to Boyle's Law and the fact that it's an indirect relationship between volume and pressure, what this should tell us is with pressure going down, our volume should be going up. So whatever answer we produce from this substitution, it ought to be greater than 315 milliliters. Let's take a look now. V2 is equal to an initial volume of 315 milliliters. Our first pressure is 101.325 kilopascals, and if I can write that in here without running out of room, there's my initial pressure. All of this is going to be over a new pressure of 84.3 kilopascals. Notice that with every substitution, it's not just a numerical value, it's units. And notice furthermore that kilopascals are going to cancel out here. That's going to leave me with milliliters, and that is an acceptable unit of volume. V2, according to my calculator, is 378
Nice try, Charlie Brown.
378.6 milliliters. Put that into scientific notation with 3 significant digits, and yes, I expect you to put these things into scientific notation. That's going to be 3.79 times 10 to the second milliliters. And now to our second Boyle's Law sample problem. If 5.6 liters of gas in a piston has a pressure of 1.5 atmosphere, what will the new pressure be if the gas is compressed until its volume is 4.8 liters at a constant temperature? And there's that reminder once again that for Boyle's Law to be true, it's got to be at constant temperature. Let's go through and identify our variables here. 5.6 liters. Liters is a unit of volume, so there's V1. Okay, It's at a pressure of 1.5 atmospheres. There's P1. And we want to know what the new pressure, okay, we're looking for P2 in this case. What that new pressure is going to be if we reduce the volume to 4.8 liters. So there's V2. So going back to Boyle's law, V1 P1 equals V2 P2. We do our rearrangement, we end up with V1 P1 over V2 equals P2. Okay, let's start the substitution. V1, 5.6 liters. P1, 1.5 atmospheres. All of this over an initial, or excuse me, a second volume of 4.8 liters. And all of that is equal to whatever P2 is. And notice, liters and liters are going to cancel. That's going to leave me with a unit of pressure. And before I bother to crank out an answer on my calculator, what do you anticipate happening? Remember, make some sense of this. The volume is going down. What does the pressure have to do according to Boyle's law? Keep in mind, it's an indirect relationship. So if my volume is going down, my pressure has to be going up. And in fact, my calculator tells me it's 1.75 atmospheres is my new pressure. Is that an increase from the initial? Well, the initial was 1.5 atmospheres, so yes, my pressure is going up, and that is what we would expect if I've got a decrease in volume. Here are your two Boyle's Law practice problems. In the first one, you solve for a new volume. The second one, you solve for a pressure. Good luck.
That's it. I'm getting out of here.